All right, so let's get started. So my name is Dr. Lopez, Marco Lopez. I'm a postdoc in the math department, and I do research in dynamical systems, discrete dynamical systems, and fractal geometry, and ergodic theory, so basically a combination of those three things. Today, we're going to focus mostly on fractal geometry, just a very intro to fractal geometry. And we will also talk a little bit about dynamical systems because we will use those to generate fractal images. So let's get started with that. Okay, so I hope my computer wasn't very responsive before. I hope that when I write on here, it's fine. So, okay, that looks okay. So let's begin by introducing iterated function systems. So, yeah. I'm sorry? Oh, no, I postdoc. Uh, oh, yeah. I'm working with Professor Miahua Yang. Yeah. Sorry. Mhm. So to define an iterated function system, okay, we'll start with some compact subset. Let's write just a compact subset of Rn. You can just consider the real line or the plane R2. We'll give some examples in a second. And so we need that to start. And we need also a finite family of contractions on X. And by that, I mean, so this is going to be parameterized by some index A. And each of these functions will be a function from X to itself. Okay. And the contraction part means that, okay, there exists a positive constant such that if you take the length of two images, that should be smaller than or equal to, actually, that C should be 1. So let's get rid of the C if it's a strict contraction. So that'll be smaller than the original, the distance of the original points, X and Y. Right. And A is just in some index set, finite index set. So we have finitely many of these functions. You can call them F1, F2, F3, or however many we have of them. Okay. An example we're going to keep coming back to. So maybe one of the simplest examples. Let's see. Let's say X. Let me write this in. Just the unit interval 0, 1. And let's say, I'm going to call this F0 and F1, or sorry, F0 and F2. You'll see in a second why I'm skipping 1. Both of them functions from the interval to itself, defined in this way. So F0 of X will be 1/3 X, and F2 of X, 1/3 X plus 2/3. We can code both of these as 1/3 x plus a over 3, where a is either 0 or 2 in this case. Okay, so that's an example of an iterated function system. Why do we call it iterated? I haven't gotten to that part, so that'll be the next thing. So, so we can iterate these functions in the following way. So you can compose f(a)(2) with, actually, let me think for a second how I want to write this. Yes, f(a)(1) composed with f(a)(2), where a1 and a2 are any elements in my indexing set. So there's basically 4 possibilities here. I can have a1 and a2 be 0 and 2, or they can both be 0, or they can both be 2, or I can have them to be 2 and 0, right? So all of those 4 maps would be here. Now, if we want to iterate more than just 2 functions, we need a more convenient notation to use. So, okay, let's see. Let's define. So this is the set of n-tuples with coordinates in I. So this is just also known as the Cartesian product of this set. So for example, right, I2 will be the set of all pairs 0, 0, 0, 2, 2, 2, 2, 0, right? And then I3, all the n-tuples, okay, I'll just write A1, A2, A3, such that A1, A2, and A3 are any elements in I. This is a way to code the maps of my system. So if, let's say now, let W be any, you can think of this as a vector, right? N-dimensional vector whose coordinates come from I. And having this defined, we can define, Fn omega. So yeah, omega is something like that. So Fn omega will be the map F omega 1 composed with F omega 2 composed, etc., all the way up to F omega n. Okay, and in every case, if we go back to the example, every one of these maps is one of these 2 maps, right? F0 or F2. Okay, so this basically defines a dynamical system, although we won't really get into the dynamics part, but you can think of, you can pick a point x, and then if you calculate F omega n of x, that'll give you another point where the original point has moved to after time n. And as you increase n, this point keeps moving around. Right? So in that sense, it is a dynamical system, a discrete dynamical system, because we're only looking at discrete values of time, 1, 2, 3, 4, etc. But right now, what I want to focus on is on certain sets that are generated by these iterated function systems. Okay. So maybe you guys are already familiar with the Cantor middle third set. So which we will define in this way. So we'll start with Z0 being the interval 0, 1, right, which is just this line segment. And then in the next step, I'm going to take the middle 1/3 and I'm going to erase it. So I'll end up with this interval and that interval if I erase the open middle interval of length 1/3. I'm going to call that set C1. So this is going to be 0, 1/3 union 2/3 1. And then to each interval, I'm going to repeat this process and erase the middle third again. So I'm going to end up with 4 intervals like this. I'll call that C2, etc. So what is going to be the Cantor set? So now define. If you guys want me to go back, if I move too fast from a page or something, you want me to go back, just let me know. So although the recording should also be available, right? So the middle third is going to be basically, if I repeat this process ad infinitum, whatever points that are left that are never removed, basically, those are going to be my set. So that's going to be the intersection of all of these sets. Okay. This is yeah. So yeah, maybe this is not necessary. But maybe one remark is, notice we have a nested sequence of sets. So C0 contains C1, and C1 contains C2, etc. Have you guys seen this set before in any class, or maybe just like not in a class? First time, some people have seen it, okay? Sometimes in a class in real analysis, you might see it as an example. It's non-empty, maybe that's not so obvious, but if you think about it, the point 0, the endpoints of this interval will never be removed because we're only removing the middle. So at least the point 0 and 1 will be in the set, so it's not empty. Not only is it not empty, it's also infinite because, okay, you can apply the same reasoning to the 1/3 and 2/3 points. Those will never be removed. And so we'll have an infinite set, at least countable. It takes a little bit more work to show that it's actually an uncountable set. C is uncountable, but contains or does not contain any open intervals. Right. The only closed intervals are singleton sets. So it's a set that has interesting properties. Okay, what does this have to do with the iterated function system? So the iterated function system I was talking about in the previous example can be used to construct this set. And similar iterated function systems can be used to construct other fractal sets. This is an example of a fractal set. So let me say something about that. So back to our, I'm gonna abbreviate iterated function system by IFS. So if you graph the two functions, their graphs look like this. This is the graph of F2 and this is the graph of F0. Oh, sorry. That's not right. I drew them. They have slope 1/3, so I should put this 1/3 here and 2/3 here. And the graph of the first one looks like this, and the graph of the other one looks like this. This is F0. This is F2. Right. Each one has slope 1/3, y-intercept 0, and y-intercept 2/3. Okay. Then what? So notice that F0, the image of the interval 0, 1, it's this interval here. So this whole interval 0, 1 here, the image of that under F0 is this interval here. 0, 1. Or sorry, 1/3. And F2, 0, 1 is 2/3, 1. This interval here. That gives me C1, right? Basically, the union of those two images gives me C1. And then how do I get C2? Well, now I take the image of this under the two maps, and I'll get one of these two sets and one of these two sets. So actually, let's write right here. Oops, no. Okay, how do I get rid? Okay, let's see. This is the image of X, the interval. Okay. What is this one going to be? This is going to be the composition of F0 composed with F0 of X. What about this one over here? It's not a very good, these two should have the same length roughly. Right. So this should have a length 1/9 and length 1/9. This also should be the composition of two maps. But in which order should they be? 0, 2 or 2, 0 or? Any idea? So if you look at the inside, the first map, okay, this interval is a subset of F0X. Therefore, basically, this first image should be this interval. So this one should be 0. Because I need that set to be a subset of F0X. And then this one will be 2, 0, 2. Okay. This one here will be F0 composed with F2. And this one here will be F2 composed with F2. Okay. And so on. So Cn in general will be the union of, how do I write this? Actually, let's write it for C2 first. Oops. Is going to be the union of F. Let's use the notation we already invented, which was F omega n x. Right. Notice I'm using the coordinates 2, 0, 0, 2, also 0, 0, 2, 2. Those are all the coordinates in this set, I2. So union over all elements in I2. And this n should be a 2 also. Okay. In general, Cn is equal to the union over all, let's say, vectors of length n and images of compositions of n maps of x. Remember, x is the interval 0, 1. Okay. Okay. Oh, I forgot I had this page too. So maybe it would have made more sense to write this here after I wrote that. Okay. So in general, yeah, Cn is equal to the union F omega n of the interval 0, 1. And the Cantor set is the intersection over all n. Okay. So basically, using this formula, we can replace the functions in our example with any function as long as it's a contraction. And define a new set in pretty much using the exact same expression here. And usually under some conditions, this will turn out to be a fractal also. Okay. So in general, for any IFS, we call this the limit set. Will be this. Now, x doesn't have to be the unit interval. It can be a subset of R2, for example, the unit square or something. And instead of having two functions, F0 and F2, you can have any number of functions. And we can still define that set there. And then I'll write here, usually a fraction. Oh, sorry, a fractal set. And why usually I need some extra conditions to make it a fractal set, like I need fa of x closure. Well, let's see. Yeah, that's fine. Intersection of a fb of x to be empty. So I don't want the images to overlap. And as long as these images are separated, we will have a fractal pretty much guaranteed. Let's see, sufficient condition. This is called some separation condition. Okay. So any questions? So it's a fractal subset of x, which doesn't have to be 0, 1. Right? In the example, it was 0, 1, but x, actually, let's look at maybe some other example. So it's the limit set because we have this sequence of sets, Cn equal to omega in Im, f omega in x. And it's a decreasing sequence in the sense that Cn will contain the next one, which will contain Cn plus 1. And in a certain sense, when you take the intersection, it's like taking the limit of the sequence. We can be even more formal and define a metric on the collection of compact subsets. And in this metric, this sequence will converge to an element. It'll be a complete metric, so the limit will be part of the space. And so in a really strict sense, it is a limit. But I'm not going to define that metric. It's called the Hausdorff metric, if you want to look it up. So C is equal to the limit as n goes to infinity of Cn under this metric. Okay. Okay. Maybe an example in R2, let's say x equals the unit squared, right? So the set of all x and y in R2 such that both x and y are between 0 and 1. So, okay. And let's say I define a function. Let's say my indexing set will be 1, 2, 3, 4. And then maybe I'll have you think what the functions are. I'll just draw the image. So let's start with C0 will be the whole square, just x. We always start with the whole set x. And then to draw C1, okay, I'm going to split this into 16 squares, all of the same size. Okay, so I've partitioned this into 16 little squares, and I'm going to pick some of them. I'm going to pick 4 of them. Let's say I'm going to use this one, this one. Sorry? You definitely could. It's just the example, the particular example I'm picking. But you can definitely subdivide this big square into any number of squares and pick some subset of those. Yeah. And I'm going to pick that one. And I'm going to pick that one too. So 4 of them. And let's say this one will be the image under the first map. We'll go by columns here. So this will be the second image of X. And then this one will be F3 of X. F4 of X. Okay. So ignore the black lines here. Those are not part of the set C1. Only the pink regions are part of the set. Well, it includes the boundaries too here. So they are closed sets. Okay, what will C2 look like? That's right. Let's see. That's going to be a little hard to draw, but I'm going to try. Oops. Well, let me draw the square first. Okay, so let's see. Now, each of those 4 pink squares that I drew, I'm going to subdivide into 16. Right. And now I'm going to pick the right one. So this one, this one, this one, and this one. And then I do the same with all the other ones. So some square here, some square here, some square here, and some square here, and so on. So and same thing here. Okay, that'll be C2. And we can get rid of the black lines to make things a little bit, okay. Oops, I erased too much. But that'll be C2. And then if I continue this process, I'm going to get smaller and smaller sets. But it's going to be non-empty, right? Each of these sets is a compact set, and I have a nested sequence of compact sets. There's a theorem in topology or analysis that says that the intersection of all of those will be non-empty. Okay, so there will be something left. Okay, so maybe a question for you to think about is, what are the 4 maps that generate this image? So F1, F2, F3, F4. So this is called, let's see, coding. Finding these maps is coding the image. If we go in the opposite direction, if you start with the maps and you want to find the image, that's decoding the image. Okay. Okay. That's C2. Okay, so that's fractal sets generated by iterated function systems. Now we want to, let's talk about dimension of geometric figures. So, okay, I wrote 10 pages of notes. That was all just the first page. And we only have 12 minutes left, so, but it's okay if we run out of time, as long as we hit the main ideas. So let's talk about dimension. Let's see, fractal dimension. So let's start with the dimension of some familiar objects already. So geometric objects. So let's start with a line segment. It can be an infinite line or just a finite segment, such as the interval 0, 1. What would you say the dimension of this line segment is? 1, yeah. Roughly speaking, you need only one coordinate to specify a position on this line. That's the number of coordinates tells you the dimension. 1 dimension. Let's also consider its size. In this case, if we're talking about a line segment, we would consider its length. Okay. If we now consider something in higher dimensions like a square, oops. Right, that's okay, and its interior. This has 2 dimensions. And when we talk about its size, now we talk about its area. Right? You can also talk about perimeter, but area is a better notion, right? You can have a perimeter extremely large, but a tiny area, and probably areas. Okay. So we're sort of using these dimensions because they are already kind of familiar with us, but we need a formal definition of dimension that we can apply to fractals as well. So if we go back to 1, okay, so we need to define n epsilon be the number or the smallest number of balls, closed balls, with radius epsilon. The smallest number of closed balls of radius epsilon that cover our set F. So some subset of X. Okay. So let's go back to the line segment 0, 1, and let's say this is X. Actually, let's say that's also F. Let's not consider a fractal, just the whole interval. And let's say epsilon is equal to 2 or 1/2. Then how many balls do we need to cover this interval? 2, right? You can have these 2 intervals. Yeah. Well, that's just the same figure above. Right. And now if we choose, let's say epsilon equal to 1/10, Okay, that's 5. Tenth. Then n epsilon is 10. And in general, n epsilon here is going to be approximately the same as epsilon. We'll write a constant times epsilon. Actually, exactly epsilon in this case. But if we consider different things, the common property is going to be approximately a constant times epsilon to the first power. Now, let's think about the square now. So whatever that number is, if we cover, it's a little trickier with the square because we cannot nicely cover it with balls, with circles, right? There's going to be, we're going to cover more than just the square. But let's just think, okay, whatever that number is, cover X with the smallest number possible of balls of radius epsilon. Then the area of the cover will be equal to the number of balls times the area of each ball, which is pi r squared, or epsilon squared, because that's the radius, which is again some constant times n epsilon, epsilon squared. Okay, that's just going to be 1, the area of the square. But okay, as epsilon goes to 0, what happens? So when we cover the square with balls, right, the area of the balls is going to be larger than the area of the square because we're going to be covering a little more than just the square. However, as epsilon gets smaller, more or less intuitively, that excess area should go to 0. We should be able to more efficiently cover the square. Yeah.
So the area cover equals whatever n times pi epsilon squared. But like if we're trying to cover like a square with circles, like don't we have overlaps of the circles?
Yes, you're right. You're right. So actually, let's say it's going to be less than. Okay, we can say that. Okay. It's going to be less than, yeah. But anyway, as epsilon goes to 0, we would expect that the area of the cover to converge to the area of X. Okay. So if we continue this process with, notice that this is an exponent of 2 now, as opposed to exponent 1, which was for the line here. In general, okay, in general, so, or subset, let's say, let's continue using squares, but now higher dimension. I didn't write something here, which is, yeah, so basically from this, we should get that something like a constant times n of epsilon squared, should converge to 1 as epsilon goes to 0. And then same thing here, a constant times epsilon to the n should converge to the volume of x, which is 1. Okay. So if we apply this, okay, this is, again, I wasn't very rigorous, like it was pointed out here, this is smaller than, but if we work a little harder, we can prove that this is true. So in general, so we can, to come up with a definition of dimension, we can demand that this is also true for fractal sets, okay? So let's require this property holds for any set, any compact. The compactness is important. Compact subset of X. That is C. Okay, so now this is the dimension. And it's right here. F subset of X. And whatever the dimension of that fractal set is, we'll write it as D times, or sorry, that shouldn't, that's not where the exponent goes. Let's say, yeah, let's just say 1. Okay, we don't have any time left, so basically, but you can rewrite this as D can be the limit as epsilon goes to 0 of the natural log of n epsilon divided by the natural log of 1 over epsilon. So if the limit exists, this is called the box dimension. And just to finish, I was going to go through the whole detail, but I'll just give you the result. So for the Cantor set, the dimension is log 2 over log 3. Which is approximately equal to 0.6 or something like that. 0.631. So as opposed to more familiar figures, we don't get a clean integer dimension like 1, 2, 3, 4. That's why we call these fractals, because of their fractional dimension. And then the other subset of the square in the example, what was the dimension of that? I think it was 1 dimension. Yeah. So it doesn't contain any line segments, but it actually has the same dimension as a line segment. Okay, I wish I could show the details of those computations. It's not too hard, but time is up. If you have any questions about this, how we got these results, feel free to email me. I'll also just drop some references here. There's, if you're interested in this topic, books by Barnsley. This is maybe the most intro level. Fractals Everywhere is the name. And then there's also 2 books by Falconer. One of them has a pretty long title, I forget. The second one, which is slightly more advanced, it's called Techniques in Fractal Geometry. And then, let's see. I think I have the book somewhere here. No, I don't have. Okay, I don't have the book here. I forget the title of the first book, but it has the word fractal in the title somewhere, so you can easily find it. There's definitely much more I wanted to say. Box dimension is not the only definition of dimension. It has its limitations. It has some properties that are kind of counterintuitive. So there are better definitions of dimension. The nice thing about box dimension is that it's relatively easy to calculate. Hausdorff dimension is very, very difficult to calculate, but it has much nicer properties. It doesn't have some counterintuitive properties. Okay, so I guess I'll stop here. Yeah, thanks. Thank you. Are there any questions? I guess. All right, thanks.